This conference will now be recorded.
Okay, thank you very much for being with us today, for participating in this seminar organized by the Retrace Proceeds and Just to See projects. It is our honor today to have with us Dr. Borja Ponte. Borja is a lecturer in business administration at the University of Oviedo in Spain, and before this, he worked for a long time in the UK at Cardiff Business School first as a research associate on a circular economy project where also the European Remanufacturing network was participating. And then he also worked at the Open University as a lecturer in operations management. Borja research deals with the dynamics and economic performance of supply chains, and recently Borja's main interest has been focusing on the translation of circular economy principles in supply chain operations, specifically looking at closed loop supply chains. Borja is an author of several papers on the topic. He has been publishing in very prestigious international journals, such as International Journal of Production Research, Computers and Operations Research, International Journal of Production Economics, Omega, you name them. And recently, together, we have also been co-guest editing a special issue in International Journal of Production Economics, whose main aim was to fill a gap in the closed-loop supply chain management literature that was related to the lack of empirically grounded research. We have now completed almost the editorial process for this special issue, and we will be soon putting an editorial together for this. So looking forward to it, Borja. Without losing more time, I ask Borja to start with this talk, which I suppose will be of great interest to many of our early stage researchers from the Retrace network who are here in attendance today. Over to you, Borja.
Thank you very much, Andrea, first of all, for the invitation to be here with you. I'm very happy to be here with you in this interesting seminars that you organize. So thank you very much. And yes, I'm going to speak today about a little bit about the dynamics of closed loop supply chains, which is mainly what I have been researching in the last 3-4 years or something like that. And specifically, the presentation that I'm going to do today is going to be based on an article. You can see the article at the bottom of this slide. It's called Quality Grading of Returns and the Dynamics of Remanufacturing, that I published a year ago in the International Journal of Production Economics, together with my colleague Salvatore Canele from the University of Catania, Roberto Dominguez from the University of Seville, and Professor Mohamed Naim and Professor Aris Sindetos from Cardiff University. So basically, although I will also be considering other parts of the dynamics of closed loop supply chains, I will be mainly focusing on the findings and implications that we obtained from this specific article. So this is what I'm going to, this is how I have structured this presentation. First, I'm going to provide you with a little bit of personal background. Thanks, Andrea, for making let's say a brief presentation of what I have done so far. but again, I want to explain in less than 5 minutes my links to the circular economy. I'm sure that most of you don't know me, so I want to first to start by saying who I am and how I have been linked to the circular economy so far. Second, before moving directly to the article, I want to explain a little bit, let's say, the pillars of our research to provide some context about how we do in terms of supply chain dynamics. I'm sure that some of you may know what we refer by supply chain dynamics. Maybe others don't know exactly what it is. So I want to provide some context to understand a little bit better the article that I'm going to explain in the following points. So in the third point, I'm going to speak a little bit about the motivation and the goals of this work that, again, I have published with other colleagues from other universities in the International Journal of Production Economics 1 year ago. Then I'm going to explain you how we have modeled this problem. Now, once we have explained the problem, how we have modeled this problem using control theoretical techniques, then we are going to move to the results. First, we are going to do what is called the steady state or the static analysis, and then I'm going to focus on the dynamics analysis. And then at the end of this presentation, I'm going to focus on the findings, implication, and future research directions that emerge from this work. So again, to provide some personal background, as I understand that most of you don't know me. I'm from the north of Spain. I'm from a region in the northwest of Spain, which is called Asturias. No? Maybe some of you have heard at some point about Asturias. I'm sure that many others have not, because it is not one of the most popular parts of Spain. Indeed, for example, in terms of weather, we are more like the UK than like Spain. No? So it rains a lot here, and so it's not like the typical sunny Spain, to say something. And I studied industrial engineering, specifically, or let's say with an expertise in industrial management, and I did my PhD, which was called bullwhip effect reduction through artificial intelligence techniques. So basically, I studied the dynamic behavior of traditional supply chains, no? Without, let's say, the reverse logistic, without the closed loop structure. As you have said before, in 2017, in January, I joined a EPSRC-funded project, which was called Resilient Remanufacturing Network Forecasting Informatics and Hollands in the university, or in Cardiff University. So I moved to the UK in January 2017, where we formed a small team of 6 academics, 3 young academics and 3 senior academics, that you can see in the photo. I always use this photo to speak about our project because Ying, Mo, and Aris like this photo very much, because the senior academics are like very happy and the young academics are like very serious. So this establishes a difference in some way in the different stages of academic life. So they used to make a joke with when I use this photo in our presentation. And it was an EPSRC project, as I said before, where we had the opportunity to collaborate also with important companies in the UK, like BT, also others like Brother, MCT, Kioptic, which is a pure remanufacturing, Panalpina, and also we had the opportunity to collaborate with 2 policy advisors that you can see here, as Andreas told before. So this is, in this project, I want to speak now about this project because this is the project through which I started to work. I can see some noise. I'm not sure if. Okay. So yeah, I wanted to speak a little bit about this project because, as I said before, in my PhD, I was studying the dynamics of traditional supply chains. Basically, in this project, I changed the scope of the supply chain. So I moved to study closed loop supply chains, but let's say I was doing exactly the same. So basically focusing on the dynamics and economics of this system. Now I'm going to explain in a few minutes what do we refer by the dynamics of supply chains. So I wanted to speak also about this project because the article that I'm going to discuss in this presentation started at this moment in 2018. No, we started this article with a visit of Salvatore Canella, who works in the University of Catania. He came to visit us in the UK, and we started having some discussions about the problem that we are going to try to solve with this article that we finally published it 3 years later. Finally, or after being in Cardiff, I moved to Milton Keynes. I'm sure that those of you that live in the UK know Milton Keynes. It's a modern city, more or less, between London and Birmingham. I was working for 1 year and a half, more or less, as a lecturer in operations management at the Open University Business School. And after that, in 2020, just before all this pandemic started, I moved again to Asturias. So I closed my loop in some way, and I became lecturer in business administration at the Polytechnic School of Engineering of the University of Oviedo. So this is where I am working now. Again, in the university where I started. We moved back. Our family moved back to Spain mainly for personal reasons, and I'm now working in this institution. So, after this brief presentation, the pillars of our research, basically what we believe is that supply chains can be dynamically designed to improve product availability, reduce operational costs, and create a stable working environment for all actors involved. So, we can say in a very simple way that if we speak about managing the flow of materials in a supply chain, this applies both for traditional supply chain and for closed-loop supply chains. It is mainly about optimizing the satisfaction of customers while at the same time minimizing the total supply chain inventory and maximizing the stability of the supply chain operations. So again, put in a simple way, when we speak about managing the flow of materials in supply chains, what we want to achieve is to optimize the satisfaction of customers, but at the same time to keep costs as low as possible. And this affects not only inventory costs, which of course are very important, but also other types of costs which are related to the variability of the operations. So, in some way, we can say that here we have two different problems. On the one hand, we can say that we have the inventory problem, where we know very well that there is a trade-off between the level of satisfaction, so for example, between the fill rate and the inventory investment. So again, the problem of inventories is mainly about managing this trade-off, the trade-off between the fill rate, for example, you achieve, and the inventory that you are using to achieve this fill rate.
And
Hi.
good if it's French. If it's in French, so we can do the double thing.
Hi.
Sorry, Borja. I mean, I think the problem has been solved. Don't worry. There was an attendant with the open mic. That's fine.
Okay, I didn't know if I had a question or something like that. Okay, thank you. Okay, so again, here there are two very important problems that are strongly interrelated. On the one hand, we have the problem of inventories, and on the other hand, we have the problem of orders. And this is something that I want to highlight. This is something that we always highlight, let's say in the discipline of supply chain dynamics, that these problems, the problem of inventory and the problem of orders, are often analyzed independently in the literature. There are some papers that focus only on the problem of inventories, which is very important also. There are some papers that focus only on the problem of orders, for example, on the bullwhip effect, which is also a very important problem, but it is important to highlight that there are essentially two sides of the same coin. That is, both problems are strongly interrelated. So we are in some way that they need to be investigated together. The implications of the decisions about inventory need to take into consideration, again, its implications in terms of orders. No? So basically, when we speak about supply chain dynamics, which I think this is something that I always want to do at the start of my presentations to provide some context, we speak about a discipline that explores the interaction between the different elements, nodes, policies, methods, and structures, so the different elements of supply chain, by considering the evolution of the main variables that define its behavior. which again, I refer basically to inventories and orders. So in the following part of this presentation, as the key performance indicators, we are going to look at mainly two different parts. On the one hand, the perspective of inventories. So here, for example, we can see in this slide, imagine a consumer demand like that, and imagine that the net stock, so the stock, for example, of the serviceable inventory is something like that. If we compare this net stock to this consumer demand, that can be done in different ways. For example, through the net stock amplifications metric, which is basically the variance of the net stock to the variance of demand. If we analyze that, we are analyzing the problem of inventory. So basically, we are analyzing the efficiency of the supply chain in satisfying the customer. So again, this is important because it has an impact on the net profit of the supply chain. And if we look at the problem of orders, I'm sure that most of you have heard about the problem of the bullwhip effect, that is the amplification of the variability of orders in a supply chain. If a consumer demand like that results in a production rate like that, we can see that the variability of the production rate is much higher, and we can see that there has happened something in the supply chain that has amplified this variability, this problem that is known as the bullwhip effect. So again, we are going to study both perspectives in this article. And what techniques do we use to study the dynamics of supply chain? Well, there are many papers that study the dynamics of supply chains, mainly from the late 90s, with those papers that have started with exploration of the bullwhip effect, but mainly these articles use three different types of techniques. On the one hand, simulation and experimental techniques, for example, design of experiments. Also, let's say what we can call stochastic calculus, so pure mathematical techniques that study the variance, the PDFs, or the probability density functions of the different, let's say, sources of stochasticity and these kind of things, and control theory, which is what I have done in this article, and this is something that in Cardiff they have been using for a lot of years to explore the dynamics of supply chains. So basically, in control theory, again, I'm going to provide some context. What we do is to develop a mathematical model in the time domain, where the independent variable is t. Then we linearize this model. So we use different kind of techniques to build a linear model from the nonlinear original mathematical model. Then we move the problem to what we can call the Laplace domain. So basically, we transform the linear equations into equations that use the variable s, the Laplace variable. So we can call this the Laplace model. Then we build a block diagram. Then we derive the transfer functions from this block diagram. And this allows for a deep study for let's say, transfer functions facilitates an in-depth understanding of the behavior of these systems. So in this specific case, we are going to present, it's called a frequency analysis, use both diagrams that again are typical techniques in control theory that allow us to understand the behavior of the system for different types of demand signals. And at the end of the study, what we also need to do is to simulate the behavior of the mathematical model that we have developed at the start of our analysis to check that everything is well aligned. So to check that the conclusions of our analysis, that the understanding that we have obtained through control theory applies to the mathematical model that we have studied. So basically it's about, let's say, the validation of the results that we are obtaining. So again, I'm sure that some of you know a little bit about control theory, or some of you have worked with control theory, have studied control theory, others not, but again, I'm happy to provide more detail if you want at some point. So specifically, coming back to this article that I'm going to present in this presentation, which are the motivations and goals of this work? Again, as I told you before, we have started considering this problem in 2018. let's say the context is something that you know very well, that the world economy is currently evolving from a linear to a circular model. I'm sure that in this specific project, you know a lot about these kind of things. It's important to highlight that, of course, we have both environmental and economic opportunities in this that result from these emerging circular models, and as a consequence, the supply chain paradigm is shifting into a closed-loop archetype, such as the one that you can see here. So we are moving from something in terms of supply chain, from something like what we can see on the top of this slide, to something ideally without resource extraction and landfill, again, ideally, to something like what we can see at the bottom of this slide. No? So, a crucial characteristic that differentiates closed-loop supply chain context from traditional open-loop supply chain context is the uncertainty in the quantity and the quality of the returns. Now, this is something that we have discussed a lot with different of our industrial partners in that project that I did in Cardiff. Something that all of them insisted a lot is that they have to manage, they have to accommodate a lot of uncertainty, not only in the quantity of the returns, which we normally call cost, but also on the quality of the return products. So basically, this means that some products will return to the supply chain with a high quality, with an important economic value. They can be remanufactured, for example, in a relatively easy way, while others will return in a very bad condition, and they can not be returned easily to an operational state. And this is something that it is not common in traditional supply chains. This is a problem that is normally specific to these closed-loop supply chains. Only in very specific examples of traditional supply chains, they have these kind of problems with raw materials. Despite that, most studies assume a single quality grade for all returns. So if you look in the literature of closed-loop supply chain dynamics, but also generally in the literature of circular economy supply chains, it is easy to see that most studies assume a single quality grade for all cores. And this results in this sentence. I like this quote from two very big experts in this matter that say that let's say a common problem in the literature of circular economy supply chains is that we often obtain elegant solutions addressing non-existing problems, which I think is a very clear quote from the perspective that say that sometimes we academics have the issue, and this is something that also applies to my research. So this is, I think, a common problem in academia, that sometimes you develop a model which simplifies reality too much, and then you obtain, again, very elegant solutions to problems that don't exist. So this is something that has happened in general terms, in terms of when studying the quality of the uncertainty in the quality of course. A lot of simplifications are often made that in some way challenge the utility of the results. So, a question that we have asked ourselves when we started this article: to what extent does quality matter? No? If we look in the literature, for example, this quote was taken from a paper of Denisel et al. 10 years ago. They say what you can see there. Based on our conversation with the managers of the manufacturing facilities, the uncertainty in the quality of the returns presents a much larger problem than the uncertainty in the quantity of the return. So basically, they are saying that it is a very important industrial problem, the problem of the uncertainty in the quality of the returns. And to use another example also from their paper, they say that, or they reported that at IBM remanufacturing facilities, quality variation might result in a 300% difference in the required recovery time. So basically, some laptops with high quality, after their use, they can be easily and with a relatively low cost come back to an operational state, while others require much more time and much more cost to come back to the same operational state. And also speaking with some managers, indeed, this quote is based on, let's say, the conversation of the team of authors with a manager of a remanufacturer. one of the remanufacturers that I showed before, they said this sentence that, let's say, brought our attention. They said, we cost the program as a single average cost per product family, knowing that we will lose money on some returns, those with bad quality, but make money on other cores. So basically, if for that remanufacturers we represented the relationship between the unit margin, the benefit that they obtain per product, and the quality of the return, they have something like that. For those products that arrive in a very bad condition, they simply lose money because they need to invest money, for example, to inspect these products, but maybe they will not be able to remanufacture these products. For other products, for example, for other qualities, of course, they will get money that needs to compensate the money that they lose with low quality products. Also, in another article, Thikopoulos in 2017 concluded that ignoring quality uncertainty in the modeling of closed-loop supply chains results in extensive additional costs. So again, this is an important problem for organizations which have been analyzed relatively low in the literature so far. And this is like the problem statement that we are going to build to study the implications of this problem in terms of supply chain dynamics. So, another question, how can managers deal with quality uncertainties? A very common solution in practice is called as quality grading, which is basically categorizing the different returns according to their condition as soon as they arrive to the manufacturing facility. So again, there are different solutions in practice for accommodating this uncertainty in the quality of returns, but a very common solution is this, or simply to look at the cores when they arrive to our facilities and establish different categories of cores according to their state. So basically what we want is to prevent that the uncertainty in the supply of returns translate into process uncertainty. So we want to accommodate, as I said before, the uncertainty before it enters the process. So this is a very common solution in practice, and what we want to do in this study is to study their implications in terms of closed-loop supply chain dynamics. Before that, I want to highlight that the effect of the variable quality of cores or the value of quality grading has indeed been explored from different perspectives in the literature. And here I have some papers, some good examples. There are some very good papers that have considered the value of quality grading from other perspectives. For example, the paper by Ferguson et al. in 2009, who estimated the cost effectiveness of quality-based categorization of returns by considering the cost of remanufacturing, the holding cost, and the unit salvage value of course. From this paper, which is maybe the best paper that have been written so far on the value of quality grading, in this paper it's published, I don't remember, I think it was Management Science, so it's a very, very good paper, to the recent paper by Yannikoglu and Denisel, who studied the same problem when the quality of course cannot be perfectly known at inspection. So they assume that at inspection you cannot know with 100% accuracy the level, the appropriate level of quality for each core. From those prior papers to these papers, to this recent paper, different works have studied the value of quality grading as well as the implication of the variable quality of course. But none of these works have considered what I have discussed so far as supply chain dynamics. So basically our research question is the one that you can see there. Put this research question in a simple way. How does quality grading impact on the dynamic behavior of closed-loop supply chain? So the dynamic behavior of closed-loop supply chain have been, let's say, widely explored so far in the last decade, but none of these papers have considered the impact of this common mechanism in practice, which is known again as quality grading. So again, we are going to look at the problem from two different perspectives, the perspective of order variability and the perspective of inventory variability. We believe that the understanding of the dynamic consequences of quality grading in closed-loop supply chains would allow for a better design of these systems. So this is what we want. We want to understand the impact of quality grading on the dynamics and economics of closed-loop supply chain in order to help remanufacturers better design their closed-loop supply chain. So once we have explained the goal of this research, which can be summarized in the simple question that we have here, which is the supply chain, the closed-loop supply chain that we have modeled? Basically, we have explored a closed-loop supply chain that is based on a hybrid manufacturing remanufacturing system. So the supply chain that we have explored is like the one that you can see at the bottom of this slide. So basically, we have a manufacturing line that transforms raw materials into finished products. These finished products are used to satisfy the demand of customers, and some of the products that have been bought before, after their consumption or after their use, will return to the supply chain through a recoverable inventory. These products will be remanufactured and can be also used to satisfy the demand of customers. We selected this type of remanufacturing system, which is called a hybrid manufacturing systems, basically for two reasons. First, because this type of closed-loop supply chain has been widely investigated in the literature, so we can say that we can understand how the system behaves without the quality grading mechanism. So again, if we understand the Bayesian system, it will be easier for us to understand the implications of the quality grading mechanisms, and also because these kind of systems are relatively common in practice. Of course, there are many other types of closed-loop supply chains, but in certain contexts, for example, in the spare parts industry, you can find these kind of systems, these kinds of supply chains in practice. Now, for example, or typically, when we can say that the assumption of perfect substitution between new and manufacturing products holds. So if we can say that that remanufactured products are as good as new products, in this kind of industries, normally or a lot of times we can find hybrid manufacturing systems. So some assumptions, some important assumptions that we have adopted for this study. First of all, we have assumed that the main inventory, the serviceable inventory that has both manufactured and remanufactured products, is managed according to a proportional order up to policy, which is basically a traditional order up to policy that incorporates two additional parameters that are called the inventory controllers. The equation of this policy is the one that you can see there. Specifically, we have used an adaptation of this policy to hybrid manufacturing systems that was developed in 2005 by Tan and Naim, which basically, again, is an adaptation of the traditional order up to policy that considers two additional parameters that allows for finding an appropriate trade-off between order and inventory variability. So basically, this is a policy that is very used or is widely used in supply chain dynamics studies because it's able to provide, as I said before, an appropriate trade-off between the two different perspectives that I have been constantly spoken so far. And this is a policy that has been used in different companies. For example, in Tesco, there is a paper that you can find in the internet that explains how Tesco gained a lot of benefits in the management of their inventories by adopting this proportional order up to policy. And the second key assumption about the forward flow of material that we have used is the exponential smoothing forecasting method for the demand. We have selected this method basically because it is a popular method in practice. I want to highlight that in this paper, we want to explore the behavior of the system for different types of demands. So we basically selected a popular method in practice. It's totally true that for a specific types of demands, there are other methods that work much better than the simple exponential smoothing, but again, to be able to, let's say, generalize some results and also to understand, let's say, the general behavior of different types of demand, we have selected this popular method in practice. And other assumptions relevant about the reverse flow of materials. In this case, again, the reverse flow of material. We have assumed that the reverse flow of materials, specifically the recoverable inventory, is working according to a push policy. So basically, it means that the products are remanufactured as soon as they are available. This is a common assumption also in this kind of works, because we can say that this assumption, this decision in practice, fits well with the ethics of sustainability. In some way, it allows to prioritize remanufactured over new items, so it is a reasonable assumption. To be honest, it is not the best policy for the remanufacturer. Again, we can obtain better policies, but it is quite used in practice. So to understand the behavior of many systems in the real world, this is something that we have adopted for our study. And also, to keep things relatively simple, relatively simple, we have defined 3 different categories of returns. So basically, if you look at this figure in the right part of the slide, you can see that we have the demand. Some of these products, some of the products that are sold, which rate is defined by the return yield, some of these products will come back to the supply chain after a delay, which we call TC, consumption time. So some of the demand will be transformed into returns, and returns are inspected once they arrive at manufacturing facilities, and we assume that the manufacturer are using or is using 3 different types of qualities. High quality cores for those cores that are in a better conditions, low quality cores for those cores that can be remanufactured but are not in a very good condition, and beyond economical repair for those cores that cannot be remanufactured, so they leave the system for cannibalization purposes. Again, it is important to highlight that as it is reasonable, we are taking 2 different lead times, 2 different remanufacturing lead times for processing the high quality cores and the low quality cores. Typically, low quality cores will demand a higher lead time, a longer lead time. They will demand more time and more cost to be as good as new products. So the remanufacturing of low quality cores will demand more time and more cost than the remanufacturing of high quality cores. So again, we are using 3 different categories of returns to investigate the implications of this scheme, of these quality grading mechanisms on the dynamics of the closed loop supply chain. So as I told before, once we have the system in the time domain, we needed to, using Laplace transform and control-theoretic techniques, we needed to build a block diagram representation of the system, which is, let's say, a nice way of putting all the variables together. Here, for example, we can see that the remanufacturing process are represented. You can see on the top part of this slide, you can see that the remanufacturing process is represented that way. For example, the demand forecasting has a different way of representation in a block diagram. Again, you can see that the lines represent the key variables and the boxes represent the key processes of the system as well as the key parameters. So basically, again, the boxes represent the relationship between the different variables. So again, I'm not going to provide a lot of detail. If somebody wants, of course, I'm happy to provide more detail, or also you, of course, please feel free to write to me and I will be happy to share with you more information or some documentation about this kind of techniques and so on. So basically, again, what we can see now is a representation of the relationship between all the relevant variables in the hybrid manufacturing remanufacturing system. And with this block diagram representation, we can build the transfer function, which look quite let's say, convoluted in some way. You know? For example, this transfer function represents the relationship between the orders and the demand in the previous block diagram. It depends on Tm, which is the manufacturing lead time, Ti, which refers to the inventory controller of the proportional order up to policy. So again, it depends on all the parameters of the system, and it might look a little bit convoluted, but again, the positive things about transfer function is that in an only expression, in an only function, it expresses the relationship between two variables. And this is something that in the time domain we cannot achieve unless the system is very, very easy. In the time domain, we can play with systems of equations, but it is not possible to reduce the behavior of the whole system to a simple equation. That is something that we can do in the Laplace domain. And in the same way, we can look for the relationship between the net stock, that is the serviceable inventory, and the demand through the same kind of expressions. So basically, in MATLAB, what we are going to do is to study these two different transfer functions whose properties allows us to understand the implications of quality grading on the dynamics of closed-loop supply chains. So after that, I'm going to move to the results. The most interesting part of the results are the dynamic analysis, but in control theoretical studies, before studying the dynamic behavior of the system, it is important to check the stability of the system. Basically, to check the stability of the system, you have to study the position of the poles of the system in the complex plane, and if the position of the pole of the system in the complex plane are in the negative part of the plane, the system is stable. If there is one or more poles in the positive part of the plane, the system of the complex plane, the system will not be stable. So in this case, again, there are more technical details in the paper. I'm going to focus only on the main conclusion of the stability analysis, which is that the system is stable for all the possible logical combination of its parameters. So if we are thinking in negative lead times, for example, the system might not be stable, but it does not have a clear practical meaning. A negative manufacturing lead time, for example, has not a clear practical meaning, so we are not going to consider in our study this kind of scenarios. So basically, again, the conclusion of the stability analysis is that the system is stable for all the possible logical combination of its parameters. Also, an interesting thing about the steady state or static analysis is that you can study how to control the system in an optimal manner. For example, one thing that we have done in the paper is to obtain the optimal TP, which is a parameter, you can see TP in the equation, is a parameter of the proportional order up to policy that defines, it's also called the estimate of the pipeline lead time, that defines the size of the work in progress, the size of the target work in progress. So again, we can use this kind of techniques to derive the optimal equation that these parameters should take in control theory, so to control the behavior of the system. And this is the equation that depends on the average return yield, depends on the manufacturing lead time, and depends on the two remanufacturing lead times. And this is, for example, the relationship between the optimal TP and beta, which is the average return yield. So for example, we can see in the left part of this diagram that when the manufacturing lead time is lower than the manufacturing lead times, in this case, the optimal TP increases as the return yield increases, while in the other, it happens the opposite. If the manufacturing lead time is higher than the remanufacturing lead time, the optimal TP decreases as the return rate increases. But again, the most interesting part about the analysis is the dynamic analysis, which allows us to understand the implications of the mechanism, of the quality grading mechanism, on the behavior of closed loop supply chains. In this case, we are going to use Bode plots, which is a representation of the amplification of the demand signal to the frequency of the demand signal. So basically, just to provide some brief introduction to the interest of these plots in the OM/OR field, if we focus on the 0 dBs, 0 decibels line, this line provides information about when the amplification ratio is 1. So basically it means that, for example, the bullwhip effect is 1. It means that the demand signal is not being amplified by the system. If we are above this line, in what we can call the amplification range, in this case, for example, bullwhip occurs. So basically it means that the system is amplifying the variability of the demand signal. If we are in the other parts, we can call it the attenuation range. We can say that the system is attenuating the demand signal. So it basically it means that the variability of the demand signal is being reduced. This is interesting particularly because it allows us to, with a simple graph, with an only graph, it allows us to understand the behavior of the system for different types of demands. If we think of an annual seasonality, for example, this is a demand with very low frequency. In this case, with annual seasonality, we can see that the system is attenuating the demand signal. For example, for medium frequency demand or mid-frequency demand, for example, weekly seasonality, something like that, we can see, this is only an example, that the system would be amplifying the demand signal. So again, the interest of this plot is that it allows us to understand the behavior of the system for different types of demands. So in our case, for example, we are going to take these values to perform the analysis. We are going to use a manufacturing lead time of 8 days. We are going to use two different manufacturing lead times of 1 day and 7 days. Again, in both cases, we are assuming that remanufacturing requires less time than manufacturing, and that remanufacturing high quality returns requires less time than remanufacturing low quality returns. We are using 1 and 7 to be able to see in a clearer amount of detail the implication of this mechanism. We are using a consumption lead time of 32 days, an average return rate of 80%. So basically it means that 4 out of each 5 products come back to the supply chain after consumption. And for the control factors, we are using a good control setting that was suggested by Tanhanaim in their study. So basically TA is 16, TI is 8, and TW is 8. And for the estimated pipeline lead time, which is the other control factor, we are using the equation that we were proposing a little bit before. So in the following minutes, I'm going to focus only in this scenario defined by these parameters, but a wider variety of scenarios has been analyzed in the paper that I have spoken to you before. So for the sake of simplicity, I'm going to be focusing only in the main ideas and only in this scenario. Again, we have obtained the Bode diagrams for both equations, so for both orders and inventory, and the main conclusions of this study are the following. In terms of order variability, the key conclusion that we have obtained is that quality grading always smooths the production rate of closed-loop supply chain. So basically, if we look at this figure and we see the benchmark, the benchmark is the system where all returns are treated as low-quality returns, because if all returns are treated in the same system, of course, this system needs to be the system with low quality returns, because the low quality line is able to process the high quality returns, but not vice versa. So we can say that the benchmark is the system. From this point, when we introduce the quality grading mechanism, we can see that the peak of the Bode diagram reduces. So basically this means that the variability of the system reduces. It moves more or less from 2 decibels, more or less in broad terms, to 0 decibels. So basically it means that the amplification of the variability of the order signal is reduced from approximately 26% to 0. Again, rough numbers. But to illustrate that, this reduction in the peak of the system means that for these signals, for mid-frequency signals, the system is being reduced, or the quality grading mechanism reduced significantly the variability in the system. As can be expected, the improvement is more pronounced as the percentage of high quality returns grows. So if you have a lot of high quality returns in the system, of course, as can be expected, the improvement will be more significant. And it is also interesting to highlight that while it always happens that the quality grading always smooths the production rate of the closed loop supply chain, the value of quality grading is higher for mid-frequency demands where the original system behaves poorly. So kindly note that for mid-frequency demands, there is this peak, so it means that the system behaves poorly for mid-frequency demands, and in this case is where we can see more clearly that quality grading always smooths the production rate of closed loop supply chain. For low frequency and high frequency demands, the improvement is moderate. And if we look at the problem of inventories, which is the one that we can see here, we can see that quality grading mainly impacts on the inventory dynamics, on the inventory behavior for low frequency demand signals. So again, in this case, the benchmark is the line that we can see, let's say the lower line of all these lines that you can see in this graph, and we can see that if we implement a quality grading mechanisms, which is represented by the other lines, we can see that the magnitude increases. So basically it means that the variability grows. So again, this is particularly interesting because improving the quality of the returns provokes a decrease in the inventory performance of the system. No? Indeed, in the paper, we have called this phenomenon a quality paradox of closed loop supply chains, which again, is apparently difficult to understand, but can be easily interpreted from the perspective of the widely documented lead time paradox in hybrid manufacturing systems. So basically, it was discovered 20 years ago that under some circumstances, the system, this kind of system, hybrid manufacturing systems, might benefit from higher remanufacturing lead times. So basically in the paper, we explain that this quality paradox, which is quite interesting, is only in some way a consequence of the well-known lead time paradox. To finish our analysis, our dynamic analysis, I want to highlight that the main ideas that we have observed through Bode plots can also be observed by analyzing the unit step response of the system. So for example, here we can see the response of the system to a unit step in demand. So what happens in the orders and inventories when the demand of the system increases by 1 unit? And basically what we can see is that using quality grading, the size of the peak also decreases. So basically it means that the system will be able, with quality grading, to respond in a more smooth way due to this mechanism. And also we can see that in terms of inventory, there is this quality paradox where the variability can increase a little bit. And just to finish, findings, implication, and next steps. Which are the 3 key findings, the 3 key implications, and the three most interesting next steps that emerge from this research. Again, I'm going to focus only on the most important things. If somebody wants to discuss a little bit more the details, I will be happy to do it after this presentation or in another moment. So the three main findings. First of all, we want to highlight that in addition to other benefits that have already been discussed in the literature, implementing a quality grading policy smooths the operation of closed-loop supply chains. But this happens especially for mid and high frequency demands, but in any case, it is interesting to highlight that if we implement a quality grading mechanism in a closed-loop supply chain, this will help us manage the system in a more efficient way. No, basically, the bullwhip effect is going to be reduced. No? You can see in these results from one of the simulations that we have performed how the demand is less amplified if we use the quality grading mechanism. You can see how orders without quality grading are more variable than the orders with quality grading. This is something that we can see in the results of one of the simulations. Second main finding, that at the same time, implementing this quality grading policy might decrease the inventory performance of the system. So again, this is related to the paradox that I mentioned before, and it can happen something like that. Now you can see there a low frequency demand signal. These results come from a yearly seasonality. And you can see how the system with quality grading suffer more from backlog. There are more backlogs or more lost sales, depending on how you want to interpret that. So the system with quality grading might have a worsened inventory performance in relationship, as we discussed before. And another thing that we have observed is that over and underestimating the pipeline lead time significantly decreases the performance of the closed-loop supply chain. This is something that, again, I'm not going to discuss in a lot of detail. I think that I have finished my hour, but it is also important to highlight that it is important to estimate the lead time, the parameter that I mentioned before, TP. It's important to estimate this parameter appropriately in order to control the dynamics of the system in an optimal way. The three key implications of our work. First of all, categorizing the income returns into several quality grades enables the development of more efficient circular economy systems. We can say that this is the main implication of our work. So, for example, in this case, the design of parallel remanufacturing structure with lines for cores in similar conditions is a useful instrument for reducing the bullwhip phenomenon in this kind of supply chains. Second point, quality grading implementation requires a firm understanding of the nature of customer demand. Something that we have been discussing so far, something that we have seen so far, is that the results depend significantly on the frequency of the demand signal. So for real organization, it is particularly important to understand the demand or the type of demand signal that they need to consider, that they need to satisfy in order to understand the positives and negatives of quality grading in their supply chains. And the third key point is that while these supply chains with quality grading have the potential to outperform the same supply chain without quality grading, it is particularly important to use information transparency to realize this potential. So this mechanism can improve the dynamics and economics of this kind of supply chains, but it happens if you know how to use the information about the different materials flows. And as future research question, there are three particularly important, in our opinion, future research questions that emerge from this work. First of all, what if new and remanufactured products are not perfect substitutes? So again, we have studied a closed-loop supply chain based on a hybrid manufacturing system, but in practice, closed-loop supply chains might take very different forms. Does the same conclusions apply for other supply chains? I think that this is a very good research question that we don't know how to answer for the moment. But we recognize that it could be a very, let's say, important research question. Second, again, our study is based, for example, on a proportional order up to policy for one of the inventories, for the serviceable inventory, is based on a push policy for the remanufacturing line. What happens with other control policies or other forecasting mechanisms? Again, it is a very particular important research question. And a third research question is what happens if the grading process, if the quality grading process is not totally accurate. We have assumed in our study that the cores are perfectly classified into the different quality grades, but what happens if it is not that way? Sometimes in practice, it is not easy at first inspection to know the real quality of the core. So what happens in cases where this assumption does not hold? So I have finished with that. Thank you very much for your attention. You have also my email account there, is ponteborja@uniobi.es. So if some of you want to discuss some of these results or some of these methods in a little bit of more detail, I would be very happy to do so. So please do not hesitate to ask me. And I have finished. I don't know if you have any questions about what I have presented so far. I'm going to stop.
Thank you very much, Borja, for this excellent and very detailed presentation. Thank you. I think you have exceeded our expectations in terms of how much you went into detail and how understandable this was to us. Thank you very much. I'm not sure whether there are questions. I have got a couple of questions myself, but I want to give precedence to other people. I don't know if there is anybody who would like to ask questions. Just open your mic and go, or write in the chat. Otherwise, I'm more than happy to kick off. Yeah, Francesco, please.
Yes, I have a good morning to everyone. I'm sorry for interrupting at the beginning, but my microphone was open. So sorry.
No.
So I have mathematical experience. I have many questions, but I will be one attracted very much my attention. You talked about the stability of the solutions, and mainly you conclude that they are mainly all stable if the parameters they enter certain zones of the complex region you described. Okay. So, but which kind of stability you are talking about? So it's kind of elliptical stabilities or are attractors? So mainly the solutions, the inventory and the order strategies, they converge to the steady state.
Yeah, basically, when I speak about the stability, it means that in all the possible combinations of the parameters, the system after the transient state returns to let's say, to a fixed state. So basically, it means that the system, yeah, that the system. So if that's in the other part of the plan, what happens is that the system goes to infinite or to minus infinite or to a state oscillating without stopping. So basically, by stability, we mean that the system achieves a final state. So it ends in some point.
Okay, so also elliptical. So I understand, like a lot of Volterra model. So you go around the steady state. And if I can, all your studies are mainly based on pure operational. So, what is the level of information about the structure of the supply chain? So, the actors in the supply chain, what they know about the geometry of the supply chain. So, because if I receive for example, if I receive something, I order something, and I have my product, I can manipulate the product in order to decrease the quality of the product. That goes back and procures some costs on the inventory of the guy that is going to remanufacture. So there is a form of manipulability of this system, or is not taken into account, is
Well, in this system, what we are assuming is basically that the manufacturer have information about the remanufacturing pipeline. So we are assuming that to make the order decision, the manufacturer, which is managing the serviceable inventory, knows the state of their manufacturing pipeline. So this is basically one of the key assumptions of our work, which we have taken from the Type 3 model of Tanja 9 paper. They studied the implications of exactly what you have said. So they studied the implication about the information visibility in the closed loop supply chain on the dynamics of the system, and they concluded that the system that behaves better is the system where the manufacturer have information about the remanufacturing pipeline, which again, in practice, it might not occur. Sometimes it might be difficult to know which is really the state of the manufacturing pipeline. In our case, we are starting from their study. So basically, we have taken their best system in terms of information visibility, and we have studied the implications of our system, or the implication of quality grading in this specific system. But it's totally true that the results, that the implication of quality grading might significantly depend on the level of information transparency in the system. Now, indeed, I have spoken before about the quality, about the lead time paradox, and the lead time paradox is something particularly interesting because it happens in some cases of information visibility, but in other cases of information visibility, it does not happen. So it significantly depends on what you have said before. So to respond to your question in a simple way, in our case, we are assuming that the manufacturer have complete information about the closed loop, and that the manufacturer has or knows how to use this information. But of course, the value of quality grading might be sensitive to this assumption. So in other kind of scenarios, it may be different.
Okay, thank you very much.
Thank you very much for your question.
Thank you, Francesco and Borja. Other questions?
Yes, I have a question, Andrea, if I may.
Yeah, please, Adrian.
Thank you very much, Borja. It was a very interesting presentation. My question was regarding the quality level that you were mentioning about. I know that there should be differences in quality level of the return products, and it might be also in the components and materials. I was wondering how we can embed this quality level in mathematical modeling while designing the closed-loop supply chain, because I know there are already some methodologies like fuzzy systems to embed like in a mathematical model.
Yeah, in our case, we have studied a simple mechanism, the quality grading. So basically, we are defining 3 different quality grades and a lead time that depends on the quality grade. But it is totally true what you have said, that it can be modeled in very different ways. For example, we can define infinite quality grades. So we can define, for example, a quality grade between 0 and 1, and we can make the lead time depend on the quality grade in more complex forms. So it is totally true what you have said, that it can be modeled in another ways. Now, for example, I have seen some papers that they do exactly what I have done, what I have explained so far. They define a quality level from 0 to 1. They randomly assign the different returns to a quality level. So basically, they create a random quality level for each return, and they create a function that relates the time and cost required to remanufacture a specific quality, a specific return, and the quality level. So it is particularly interesting, exactly what you have done, what you have suggested, because again, there are different ways of modeling this relationship. And in our case, we have only used 3 different quality levels, and we have assigned a different lead time for each of these quality levels, but it can be done in other ways. And again, I think that one interesting way of doing it is simply to assign a quality level between 0 and 1. So to understand that each return has a different quality, and to use this value of quality to create a cost and or time, a remanufacturing time, depending on that. So I think that this is a particularly interesting topic. And yeah, I mean, I think that there are different papers, and yeah, if you want, I'm happy to send one of these papers that I have mentioned to you after this presentation, because again, this is part, I think that this is a very important topic, and you can find a lot of recent papers that are trying to model this relationship. Now, in our case, we have simplified this a little bit, creating 3 different channels, but it's particularly interesting topic.
Okay, thank you very much. Yeah, I would be so grateful if you could share the paper. Thank you.
Thank you very much.
Thank you, Borja, and thank you, Azar, for the question. Unless there is any other question, I have a curiosity, but a couple of curiosities. So the first one relates really to the question that Francesco asked Borja about the supply chain visibility, the supply chain integration. As you know, in the supply chain management literature, integration plays a great role in terms of information sharing, in terms of sharing of production plans. And of course, I mean, you know, there are early indications that supply chain integration can play a role also on the performance of closed loop supply chains. What were your assumptions in terms of supply chain integration in this model? And could you, for instance, repeat the experiments with supply chain integration as a sort of control variable?
Yeah, thank you, Ms. Andrea, for your question. Yeah, this is also a very relevant topic. The problem here, at least in our opinion, is that the literature about supply chain integration is very widely developed for traditional supply chains. So there are a lot of models that allow you to integrate different echelons in traditional supply chains, but there are few papers, very few papers that explain how to appropriately integrate different echelons in closed loop supply chain. So this is a problem that we have found, because indeed we think that would be a very, very interesting topic. Indeed, our colleague Roberto, that you know very well, is trying to develop some models about the different models about supply chain integration, different models, let's say, that differ in the level of integration in the supply chain, and he is trying to do some preliminary studies to compare the behavior of different models, because this is particularly interesting. And again, I think that this is a very important topic that has been very little explored in supply chains. Again, in our case, we are using a proportional order up to policy that is using some information for the we are using a proportional order up to policy that is using some information from the reverse flow of materials. So this creates some level of integration in the system, but we can say that the level of integration is relatively low. At the end of the day, both inventories are working independently. In one case, we are using a proportional order up to policy. In the other case, we are using a push policy that, again, might be reasonable in practice, but we know that can be significantly improved. So this is a very, very, very relevant question. And we have been doing some work so far. For example, in one paper that I published also in that project in EUR in 2019, we were thinking how to improve the management of the reverse flow of materials, how to remove this push policy and improve the management by incorporating some level of integration. But again, we can say that so far the level of integration is relatively low, and there need to be some studies that study how to integrate both inventories or the different inventories in closed loop supply chains. So definitely, I think that it can be created a kind of additional parameter that differentiates the highly integrated supply chain and the, let's say, slightly integrated supply chain to understand the implications. Now, indeed, some recent papers have highlighted that the paradox, the lead time paradox that I have spoken before, should not occur in a highly integrated supply chain. So some recent papers it's interesting because they have highlighted that the paradox is the consequence of the lack of integration of this system. No? So again, there are very interesting things that emerge from this point.
And thank you very much, Borja. And yeah, I definitely agree with you, you know, in the sense that if you look at the literature, also the literature that defines supply chain integration, it is a concept which has defined in a concept that has been defined in the context of traditional linear supply chains. Of course, what integration means in reverse supply chains might also need to be adapted. And the other question I had was about, you know, the rebound effect. So are you assuming that remanufactured products displace the demand for virgin products? Are you thinking also, you know, of including some sort of scenario where, for instance, if the quality of the course is not great, well, this does not cannibalize entirely the demand for virgin products. How are you dealing with this?
Yeah, in our case, we are considering let's say the scenario where remanufactured products are as good as new products and they can have the same price. This
Okay.
applies to certain industrial settings, as for example the spare parts industry, as I said before. But it's totally true that in other settings things are much more complicated, because if we have two different markets, one for, let's say, new products and the other for manufactured products, there are complex interdependencies between the demand of both markets that, I mean, indeed there are, or this is something as important as, I mean, the level of importance of this topic is making some questions, or making a lot of companies to question if they should enter into manufacturing, because they are worried by the fact that remanufacturing might decrease the demand of their original products. And again, I think that this is a very relevant topic that should be studied. What happens in terms of quality grading, in terms of the dynamics of supply chain, where there are two different markets with different demands but independent demands? Very relevant topic also. Thank you very much for the question, for the suggestion, because I mean, it's true that the behavior of these systems might be totally different. Yeah, this is very interesting because you have these kind of things with closed loop supply chains that you don't have with traditional supply chain. Like, the possibilities are much more.
Absolutely. Thank you very much, Borja, for your comprehensive response. And yeah, this constitutes really a great research agenda in itself, what you were talking about. Not sure whether there is any further question from our audience. If not, we can really thank Borja for his time, for this great presentation, and for the nice debate it provoked. And of course, the recording of this seminar will be available on YouTube, so please share it on social media when you will receive the link. And once again, thank you very much, Borja, for being with us, and thank you very much for everybody for attending this seminar and for the nice contribution to the debate. Bye.
So thank you very much, Andrea, for the invitation. And again, if you want, if any of you want to discuss something in a little bit more detail, please feel free to contact me. Thank you very much.